fix that. Section 3.3. Okay, and the two main categories that we're going to look at are congruent triangles and similar triangles. Congruent meaning they have the same size and shape, and similar meaning just the same shape. Both types of relationships help us to solve application problems. Another relationship that will only work for right triangles is the Pythagorean theorem, but that is very useful as well. All right, so first let's talk about congruent triangles. So here we have two triangles, triangle ABC and triangle DEF. And these triangles are both the same size and the same shape. This is indicated with the little marks. You see how the side DE, for example, has one little dash on it, and the side AB, this is angle B up here. I don't know why it looks like it's over there. AB has one little dash, so that's indicating that the side DE is the same length as the side AB. And similarly, EF is the same length as BC, and DF is the same length as AC. Also, there's a relationship between the measures of the angles. You can see because of this little mark here that angle D and angle A have the same angle measure. So angle D is equal to angle A. Angle F is equal to angle C because they each have 2 marks. And angle E is equal to angle B because they each have 3. So when this is the case, that all the sides are equal and all the corresponding pairs of sides have equal length, and the corresponding pairs of angles have equal measure, we say that the triangles are congruent. And we can indicate this, it looks like a little equal sign with a squiggle. We say triangle ABC is congruent to triangle. Now you have to be careful here. If A is listed first, then the angle that is equal in measure must be listed first on the other triangle, so it would have to go with D. If B is listed second, then that would mean that angle E would have to be listed second here. And if angle C is listed third, that would mean angle F would have to be listed third here. So the order in which these angles are listed matters. I could also, if I chose to, instead of calling triangle ABC ABC, I could say maybe CAB. But that would mean that when I identify the relationship between the two triangles, C has to match up with F, so this is congruent to triangle F. A has to match up with D, so FD, and then E. So that would also be a correct statement. Both statements are indicating congruence, and more specifically, they're identifying how they're congruent. So we would like to know what the minimum amount of information is necessary to guarantee that two triangles are congruent. And there are certain properties that will guarantee that they're congruent. So it turns out that if you know that two sides and the angle between them are the same on two different triangles, then that means that everything's the same. So for example, if I draw a triangle A, B, C, and a triangle D, E, F, that if I take two sides like AB and AC and the angle between them, and identify that in the other triangle that there are two sides and the angle between them that are equal to the first, then that means that the two triangles are congruent. So how would we now notice that these two triangles are kind of flipped. Angle A matches up with angle F. So if I wanted to say that these two are congruent, oops. then how would I have to label the triangle? So let's say I decided to go A, B, C here. Then our congruence would be with triangle what? Well, A matches up with F, so we're definitely going to start with F. Now from A to B, we have congruence to F to E. So we would have to do F to E next. And then the only other option is D. So you see how we have to keep it in the correct order, where not only does the angles that we know are equal match up, but also the segments that we know are equal match up as well. So this would be an example of concluding that two triangles are congruent based on side, angle, side. Two sides, AB is equal to EF, and AC is equal to DF, and the angle in between, angle A is equal to angle F. Okay, it will also work to guarantee that two triangles are congruent if you know two angles and the side in between. Angle, side, angle is what that's called. If we know that those match up, then we're good to go as well. So let's say that we have two triangles. And one is, again, ABC. This one's DEF. Let's suppose that we know that angle C and angle A match up with angle E and angle D. And we know that the side between the angles are equal as well. So we have angle E is equal to angle C. We have angle D is equal to angle A. And then we have the side in between, AC, is equal to DE. So we can apply angle, side, angle, and we know that these two triangles are congruent to each other. Let's go ahead and write the labels again. So if we start with triangle ABC, what's that congruent to? So we know that angle A matches up with angle D, so we would have to start with D. Angle B is the one that's not marked, so that would have to match up with the one that's not marked on the other triangle, so that would be angle F. And angle C matches up with angle E. So we could say that triangle ABC is congruent to triangle DFE. All right, another way to guarantee that two triangles are congruent, meaning exactly the same size and shape, is if you know all three of the sides are equal. So let me draw a triangle here. Let's call this ABC. Another triangle here. Let's call this DEF. So if I tell you AB is equal to ED, AC is equal to DF, and BC is equal to EF, then this means that they are exactly the same size and shape. When I say size, I mean lengths of the sides, and that's obvious, but it turns out that this also guarantees that the angles must be the same. For example, angle C, which is between side two, the side with 2 dashes and the side with 3 dashes, has to be the same measure as F, the side with between 2 dashes and 3 dashes. The angle B, which is between the 1 and the 3 dashes, has to be the same as the angle E, which is between the 1 and the 3. And angle A, which is between the 1 and the 2, has to be the same as angle D. So triangle ABC would be congruent to triangle DEF. So you either need side, 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 side angle, side, or angle, side, angle to guarantee that you have congruence. I'm going to skip that. Okay. The other concept that we need to be familiar with triangles is when they're not necessarily the same size, but they do have the same angles. That means that they are the same shape. So, for example, you might have a little tiny triangle that looks like this and a bigger triangle that looks like this. And although they clearly don't have the same length of sides, the angles appear to match up, which gives them the same shape. Now, when that happens, although the lengths of the sides are not the same, they'll be proportionate. For example, if this little triangle that I drew, if that side is length 1 and this triangle, this side is length 2, then this triangle on the right has all sides that are double the length of the first triangle. So suppose that this triangle has sides of length 1, 2, and 3. Then it must be the case, knowing that this triangle has a side of length 2, that this one is 2, 4, and 6. All the sides are double if we know that they're the same shape, or in other words, that all their angles are the same. So that can be useful. So we'd like to know under what circumstances could we conclude that two triangles are similar. And it turns out it's enough to have any two angles be equal, which makes sense if you think about it, because if two of the angles are equal and the angles have to add up to 180, then they must all three be equal. So if two angles are equal, which we call angle, angle, this implies that angle, angle, angle are all equal. All three angles are equal, so we have similarity. All right, so let's look at how we use similar triangles. So in this example, it tells us triangle ABC is similar to triangle DEF. Now remember, that's more than just telling you the triangles are the same size, it's telling you how they're oriented. So since triangle ABC starts with A, angle A is the first angle mentioned, and triangle DEF, D is the first angle mentioned, then we know that angle A and angle D are the same. Similarly, B and E have to be the same because they're the middle letter, and the last letters are F and C, so those have to be the same. And that's important because when we're comparing these two triangles, we have to make sure that we compare sides that are between equal angles. For example, we know that side EF is between two angles that correspond to side BC. So we know there's a relationship of some sort between side EF and side BC. Similarly, there's a relationship between ED and AB because those are between the angles, those are between the angles marked with 1 and 2 marks. Okay, and then it would also be the case that DF would correspond to AC. So this correspondence is indicating not that they're equal, because look, EF has measure 8 and BC has measure 16, but rather that they're proportionate. So I'm gonna find the length of side DF in two different ways. One, I'm gonna set up a proportion. The other, I'm just gonna use reasoning. So here's what I mean. They're asking us to find DF. We just said that DF corresponds to AC. Notice that BC was 16 while EF was 8. BC is twice as big. You would have to multiply 8 by 2 to get 16. So it must be the case that AC is also twice as big. So what number would we have to multiply by 2 to get 32? If you said 16, you're correct. Side DF is actually length 16. All right, now, sometimes it's not so obvious because it's not just doubling it. Maybe you had to multiply it by some weird decimal or something to get the right length. So the way that we can solve in general is to set up a proportion where we compare the sides, and you can either set up the proportion sides of the first triangle equal to a proportion of the sides from the second triangle. We'll do it that way first. Or you can mix the sides and do sides from the first on top of the sides from the second, as long as you keep it set up so that the first is always on top and the second's always on the bottom. So here's what I mean. So from the first triangle, which I'm going to say EDF, let's use EDF as the first triangle and ABC as the other one. I guess I should say DEF. Okay. We could look at the side. The one side that we don't know that we're looking for is DF, and I'm going to make a fraction out of that, comparing it to the side we do know, which is EF, which is 8. Okay, so both of those came from the first triangle. And I'm going to set that equal to the corresponding side. So what side corresponds to DF? Well, AC corresponds to DF. So AC has a length of 32. That came from AC. And then what corresponds to EF? EF corresponds to BC, which had a length of 16. So in order to maintain the proportion, it has to be that DF divided by 8 is the same as dividing 32 by 16. By the way, you also could have set it up as 8 over DF equals 16 over 32. It doesn't matter as long as you keep as long as you keep the first triangle on one side, the second on the other, and you keep sides that correspond. The two sides that correspond are in the top, and the two sides that correspond in the bottom. Can't mix them up. In other words, you can't leave the 8 over DF and then flip the 32 over 16. Okay, so anyway, but I'm going to stick with my DF over 8 equals 32 over 16. And what we're going to do is a little trick called cross multiplying. When you have a proportion, you've probably seen this before, you can multiply the product of the means times the product of the extremes, it's called. So 8 times 32 has to be equal to 16 times DF. Now 8 times 32 would be 256, I believe. And you could multiply it out that way, but I noticed that if I divide both sides by 16, now it's going to be a little easier. I'm going to have 8 times 2 equals DF, which means DF is equal to 16, which is the conclusion we came to before. So that's one way to work it. Or you could do first triangle over second equals first triangle over second. So what I mean there is EF corresponds to BC. EF from the first triangle corresponds to BC from the second. And DF, the side we're looking for from the first triangle, corresponds to AC from the second. So that would mean that 8 over 16 equals the unknown side, I'm just going to keep as DF over 32. And if you set it up that way, you're still, when you cross multiply, going to get the same equation. 16 times DF equals 8 times 32. And you would still come to the conclusion that DF equals 16. Okay, so that's how you set up similar triangles. All right, now the Pythagorean theorem. If the two legs of a right triangle have lengths A and B, and by legs we're talking about the sides that touch the right angle in the right triangle, and the hypotenuse has length C, and the hypotenuse refers to the side opposite the right angle, which by the way is always the longest side, then the sum of the squares of the lengths of the legs is equal to the square of the hypotenuse. In other words, A squared plus B squared equals C squared. So this is nice because you don't have to have two triangles to make a comparison to get information about the lengths. You can get it just from the dimensions of the given triangle. So here we have some examples that you might come across in my math lab that involve using the Pythagorean theorem or similar triangles. So let's take a look. This problem says there are two similar triangles in the diagram. Find the unknown measurement. So remember, to have similar triangles, you have to at least know two angles that are the same. But if they tell you the triangles are similar, then you can assume that they are the same. In this case, it's kind of tricky for people to look at the diagram and see two triangles because one triangle's inside the other one. But what I recommend is that you draw them separately as you're doing your work. So I'm going to kind of pull out of the diagram the triangle OPQ. And then I'm going to draw next to it the larger triangle, which is triangle ORS. And my cat is trying to get in on the lesson here. Hold on. Okay. My triangle looks a little messy. Let's fix that. All right, so we have, let me draw it again. Triangle ORS. Okay, so PQ has length X and RS has length 90. OP has length 60 and OR has length 120 plus 60, which is 180. And we know that angle O is the same measure as angle O. And it would make sense then that angle P is the same as angle R. It looks like they might even be right angles, but they didn't say that we could assume that, so I'm not going to. All right, so we have similar triangles because they told us we do. And so I'm going to find the length of the unknown side using the fact that when we have similar triangles, and you just have to know this, that means corresponding sides are proportional. Okay, so in triangle OPQ, we have the side PQ that we're missing, and I'm going to compare that to the side OP, which we know. But that means that I have to make sure that I compare it to the sides that actually correspond. So OP appears to correspond to OR, for example. So I'm going to compare OP to OR in the second triangle. And then PQ appears to compare to RS. All right, so let's fill in what we know. We know that, well, we're calling PQ, the length of PQ, X. And we're calling, let me write it over here. And then OP is 60. And then RS is 90. And OR is 180. Okay, so now if you want, before you start cross multiplying, you could reduce, because notice that 90 goes into 90 once and 90 goes into 180 twice. If you didn't notice that, that's okay. But we can think of this as 1x over 60 equals 1 over 2. Cross multiplying then, we get 2x equals 60. Dividing both sides by 2, then x would be equal to 30. So we would put into our box in my math lab the measurement 30. Now there are multiple different ways that you could set up the proportion. I used the way that we did the first triangle. Two sides from the first triangle equal to two corresponding sides from the second triangle. Okay, another way you could have done it is this way, where we set up from the first triangle the x, from the second triangle the 90, from the first triangle the 60, and from the second triangle the 180. As long as you keep first over second, make sure that the corresponding sides are matched up.